On May 13th in Mumbai, a billboard was toppled by strong winds, resulting in the deaths of 14 people and injuries to many more. To prevent such tragedies from happening again, we need to understand the mechanisms that caused this collapse and what could have been done from a structural design perspective to prevent this terrible structural failure. By taking a closer look at the footage of the collapse, it seems that the structure failed due to poorly designed foundations, as the main hoarding structure retained most of its integrity. Furthermore, if we examine a street-level view of the structure, we can see how robust it actually was. However, before we conclude that the hoarding structure was simply too big and incapable of bearing the force produced by the wind, we should understand that whatever loads are present on the upper part of the structure must be compensated through the foundations. In simpler terms, this means having sufficient weight in the foundations, using criteria similar to that used in the design of retaining walls. Now, this implies that a structure like this can actually exist and work properly, as long as we perform the appropriate analyses and considerations. However, beyond mere speculation, and to fully understand what could have been done design-wise, it would be a good idea to reproduce this structural model and perform an overall structural analysis and wind load simulation. As usual, we will be using our favorite software, Autodesk Robot Structural Analysis Professional. Here, through the multiple pressure maps expressed in kilopascals, we can more clearly observe how the wind load is affecting the surface of the structure, and where is that the maximum loads are being produced. For this example, we are considering a wind velocity of 20 meters per second. Let's just restart this simulation to appreciate how each of the loads is being calculated by the software. Again, through the multiple pressure maps produced on the surface, we can begin to understand the behavior of the structure and determine if other factors might have contributed to its collapse. For example, after completing both the wind load simulation and dynamic analysis of the structural model, we find a subsequent displacement of 2 meters in the structure as a consequence of the wind load, with the greatest bending moments occurring along the members in the foundation, displacement which is more than enough to cause any structure to topple. So although this first analysis is relatively simple, we now have a clear point of departure for beginning to improve the design of the structure. Quite clearly, any change in the design that results in a decrease in this massive displacement would be considered a positive one. Therefore, beyond mere speculation, we can start making adjustments to this design, verifying our model at each step. Of course, this is just one of many software options available for performing this kind of analysis and simulation, but the results it offers are undoubtedly the easiest to interpret. And in this particular case, carrying out such analyses can help us prevent catastrophic structural failures in our model. Also, if you're not yet familiar with Autodesk Robot Structural Analysis Professional, I encourage you to visit our website, where you'll find a wealth of tutorials designed to help you get up to speed with this software. So by leveraging this type of analysis and simulation capabilities, we can ensure that our structural designs are robust and capable of withstanding even the most challenging conditions, ultimately preventing catastrophic events caused by inadequate analysis.